let's briefly review exponential functions. So functions that are of the form f of x equals b to the x, where b is a constant. If you're watching this for a calculus class, and this is what I'm making it for, it's going to be really, really crucial. Let me just mention the distinction between a constant versus a variable. B is just a number. It can be whatever number we want in the context, but once we pick it in a context, we're not going to vary it. We're not going to think of it as a variable within each problem. And so the B from the beginning of the alphabet, that's where we typically pick our constants from. It's very, very important that that's just a number. So for example, we could have f of x equals 2 to the x. We could have f of x equals 1/7 to the x, just for fun. We could have the famous number e to the x. That's an x. There we go. And that turns out is going to be our favorite in a calculus context. So, what do these things look like? Well, let's see. Let's do e to the x again, and let's just let the computer graph it, and then just explain why it has a certain graph, the graph that it does. So, let's see what the features are. Okay, it's got a horizontal asymptote only to the left. X equals 0, or sorry, y equals 0. The horizontal line y equals 0, the x-axis, on the left only. Okay, that's very important. And why? Well, that's what happens when you take very small numbers, or big negative numbers, very negative, let's say, and you take an exponential. And what is that about? Well, e to the minus x is 1 over e to the x. So, for example, e to the minus, let's say, 3, about where it's just disappeared there, is 1 over e to the 3, or about what happens when you take some number that's about 3, you cube it, so you get a pretty big number, 20-something, and then you take 1 over that, and so that's going to be small. Okay, so these are going to be, in general, small when x is large. And so if you have a very negative number, like minus 10, minus 100, you're going to get a small number. But notice it never crosses. It's kind of hard to tell for sure, but it never crosses. And in fact, the whole thing is always above. And that's because e to the x is always, always greater than 0. Because basically, over here, remember, we're just taking the number e and multiplying it by itself multiple times, roughly. So that's never going to be negative. And then these guys are taken by a reciprocal of that process. And so these guys are going to be greater than 0 as well. So this is really, really important. Greater than 0 always, and in particular, never, never, ever 0. And so you never have to worry about dividing by an e to the x. That's going to be very, very useful. What else? Well, let's see. As that was pretty clever. As x gets large, of course, what I was just discussing, and positive, then e to the x gets very large very quickly. You can see it's getting up to over 100 even when x is just 5. If I change the scale and I say, let's say x equals minus 15 to 15, then it's just ridiculous how big it gets. It's trying to plot the whole thing. It's going up to 60,000 by the time x is back 11. But it's not even able to come close to plotting all the way up to 15. You'd have to make the scale even bigger. Okay, that's annoying. That's an annoying thing about graphing e to the x. I can't graph for this scale. It's as good a scale as we can probably get for this function. But we don't see it here because it's too small on this scale. We don't see it here because it's too big. There's only a brief time when we see this characteristic swooping upward shape. And so that's something I could mention. It's just that e to the x, the problem is that e to the x is hard to graph well. Hard to get a good window. In some classes I go into, that's an lead-in, into things like semi-log graph paper, which is very useful. It solves that problem, but we're not going to do that in this context, in this review. Okay. What else do we know about e to the x? Well, and I've been focusing on e, but let's go ahead and go back to some of the other bases. How do they compare? So let's do a multiple graph let's do e to the x again, but then I'm going to add in some graphs with different bases. And then I'll mention briefly why is e so important. So I'm going to add in, let's say, 2 to the x, and graph that. Okay, 2 to the x, 2 to the 2 to the 1 is 2, e to the 1 is e, so it's the bottom one that's 2 to the x. Notice it's growing slower. 2 to the 5th, still, that's only 32. E to the 5th is substantially bigger, about 150. So when that base is smaller, it's going to grow slower. So what about something bigger? Let's even add another item. Let's say 3 to the x. That's going to be this new one. Notice the scale has changed. Now 3 to the 5th is 243. It's up here almost at 250. So here's 3 to the x, here's e to the x, here's 2 to the x. And just based on those powers, the bases rather, these functions grow or decay at a different rate. But one important thing is that they're not qualitatively different. The qualitatively different thing I could do is I could put in like a number like 1/2 to the x. Now, as x gets bigger, I'm multiplying 1/2 by itself over and over again. Here is something that starts out big for negative powers and gets small pretty quickly. And why is that? Well, 1/2 to the x. Let's see, notice one thing. This 2 to the x graph seems to have been reflected over here. But that's not what I tried to do. I put in 1/2 to the x. Well, but let's see what that is. Using rules of exponents, that's 2 to the minus 1 to the x. And then those exponents can be combined. That's 2 to the minus x. That's what happens if you take, this is the y-axis mirror reflection of 2 to the x. 2 to the x. Because we placed x with minus x. And so that's a very typical thing. If this number is smaller than 1, you're going to get a decaying exponential. And in fact, a lot of the times you'll just see it written this way, because you don't have to use the fractions. It's a little bit tidier to write it as 2 to the minus x rather than 1/2 to the x. There's nothing illegal, though, about taking any big positive number and writing it to the x. One note is we never, ever use a base that's b less than 0. It's very, very tricky. Okay, if you think about taking negative numbers, why is it? It's like negative 1 to the 1/2. That's already super tricky, because it's the square root of minus 1, and that's I. But then what about like a cube root, or to the minus 1 to the pi power, or something like that? It's very, very tricky. It can be done, but it's very tricky. Even when you know what to do, it's very tricky. So that's a brief little reminder on how the exponential function works. Let me just remind you a little bit more about the algebra, though. E to the 0, of course, is 1, because anything to the 0 is 1. We've already talked about how e to the minus x is e to the x, is 1 over e to the x. Yeah, they're not the same. Oh, stop that. Okay. And another really, really important rule is just coming from rules of exponents. If you take a sum there, it's e to the x, e to the y. And for example, like e to the 2 plus 3 is e squared times e cubed. Why is that? Well, it's just that the left-hand side is e times e times e times e times e, 5 e's. And the right-hand side is just e times e times e times e times e. Now, that's not a proof for all possible exponents, but it explains why this interesting rule would happen. That's 5 things multiplied together, 2 plus 3. Or you could just multiply 2 of them together, multiply 3, and then multiply the results. That's really what's behind this fundamental law of exponents. And it's a fundamental property of the exponential function. So briefly, why e? Why this number e? Why not just deal with like 2 to the x all the time? Well, that's something we get a hint of in a calculus class, and that's that the slopes of the e to the x function are the nicest. More precisely, the slopes of its tangent lines. When we calculate those, we get an amazingly nice answer. And there's other reasons, but that's really the killer app for e. That's the real reason why people use e so much, is that when we look at the slopes of the tangent lines of this e to the x function, they have very nice properties. I'm not going to give away what those properties are because I like people to discover those. Okay.